Hello everyone. This presentation is about the usage of ARM processors in future spaceflight embedded platforms. Some key points we'll go over are spaceflight embedded platforms, some examples of them, problem statement in the research article, some solutions they went over, some benefits on using unified processor architecture, power management, benchmarking, machine learning, and results with future research. Some examples of spaceflight embedded platforms are real-time embedded systems, satellite control systems, and radiation-hardened platforms. Real-time embedded systems and satellite control systems are kind of hand in hand here. They both utilize some sensors to gather data, and then the processor will determine what to do with that depending on its design and application. Radiation-hardened platforms are very important. These are platforms that have modified silicon on the transistor level that are resistant to various radiations in space. The problem statement that went over in the article covered the inefficiency of current designs, the single application aspect of current designs, which basically means that they're not able to reuse certain designs across many different missions, which is very costly and requires much more development. Another big issue they found is the lack of reliability in some of the systems, especially when it comes to radiation tolerance. The solution and benefits covered in the article were covered by the research on the ARM Cortex A72 processor. They found it to be very cost-effective, applicable across different missions. It is much faster to develop code for it because it's across different missions you will be using the same instruction set, and in addition to that, its performance is much higher than current implementations. Some of the benefits using unified processor architecture are the utilization of common instruction set. So across all the or many of the missions, they can use the same type of instruction set. The optimization of CPU and memory utilization, the addition of having an embedded operating system, and the ability to customize your operating system tailored to those specific missions without the need to redesign your whole architecture. Due to the ARM Cortex A72's high performance, it is also consuming a bit more power than current processors, but they do mitigate some of that consumption with utilizing power gating and domain control. What that means is basically turning on and off or putting certain subdomains into an idle state when they're not in use. You can wake up those subdomains by sending an interrupt or an event and so on. Another great thing about this processor is the ability to clear its level 2 cache without turning on additional cores, and its dynamic retention, which essentially means running at various conditions, such as having some subdomains in an idle state while some other ones are processing real data. Some of the benchmarkings that were used in this research were the dry stone benchmark, the wet stone benchmark, and the core mark benchmark. Those algorithms are accepted, or they are almost the gold standard when assessing the performance of processors. In addition to that, they've used some other custom algorithms and compression algorithms, such as your JPEG less loss algorithm, which is used for machine vision. If we take a look at some of the benchmark results, we can see that the team used 3 different processors in this test. against the ARM cortex. And when you look at the actual numbers, you can see that they are much lower than the ARM cortex's performance numbers, especially when you look at your core mark numbers. But that is also due to the lack of cores that these processors have. But there's also one more thing to mention, which is the low consumption of power on two of these processors. When you compare them to the ARM, you can see that the power consumption was much higher. However, when you compare higher frequencies, which was only able to be implemented on the MPC 85, you can see that it utilizes much more power than the ARM processor. Some additional benchmark algorithms they've used in machine learning are the MobileNet single shot detector, which basically classifies and detects objects, and they mostly measured two aspects here, which is your mean accuracy precision and your throughput or latency. Here they would take your cross-section between frames and the ratio between the cross-section and your total area of the frames. Will determine the amount of data that you can actually have. The higher the ratio, the more accurate your image is, and the tighter the bounding box, the more accurate your capture is, or the more data it contains. Here are some of the results when the ARM was compared against the MPC 85. You can see that the encoding and decoding time of these images was about 20 times faster than the MPC 85. If you look at the right side here, you can see that even when the ARM used multiple cores, the score did not really change. However, that is due to the algorithm itself, because the algorithm of the dry stone and whetstone are single-threaded. Multiple cores won't really increase the performance. However, on the core mark algorithm or benchmark, the use of multiple cores does impact the performance because they're using a multi-threaded algorithm. If you compare the MPC 85 versus the ARM on the core mark, you can see the score is about 5 times better on the ARM versus the MPC 85. Some future research that was discussed in the research paper was testing additional machine learning algorithms, benchmarks with a closer to real-time data numbers, because the synthetic algorithms can't really provide the sporadic data that sensors sometimes give into the system, as well as developing more testing for radiation resistance on the silicon layer to determine the longevity of the processor. This about concludes the research paper by the authors Kayla.Henderson, Nathan.Wiatrek, patrick.saenz from Southwest Research Institute, San Antonio, Texas. Thank you.